Good morning, my name is Elena Ferretti from the University of Bologna, Italy, and I will present you a new strengthening technique, the straps-strips technique, for load-bearing masonry walls subjected to out-of-plane loads. This technique has been developed over the last 2 years to increase the strength of buildings during a seismic event. The specific problem faced by the technique is the failure mechanism of a masonry wall when the earthquake direction is orthogonal to the wall. In this case, due to the oscillatory nature of the earthquake forces, a wall receives repeated horizontal thrust from a floor which exerts a hammering action on the wall. If the wall is retained by good upper and lower connections, while the connections between wall and floor and between wall and orthogonal walls are weak, the wall breaks into two parts with the formation of a hinge, usually at floor level. This is a very frequent damage mechanism in a masonry building and leads to either partial or global collapse, known as vertical wall bending. Thus, counteracting the vertical wall bending is of primary importance in masonry buildings. The easiest way to achieve this is to use vertical beams resting against the wall like the ancient buttresses. The purpose of the straps-strips technique is exactly to achieve this effect, but without having to build bulky buttresses. The key idea of the straps-strips technique is to exploit friction to achieve a new strengthening system. In fact, since a body does not slide on its support plane until the force acting on the body falls inside the cone of static friction, if two independent masses are pressed on the two sides of a wall, the friction forces establish a stiffness constraint between them. Therefore, the independent masses begin to work together as the two flanges of an I-beam. This means that it is possible to use flat strengthening elements useful for surface applications to build a strengthening system that acts in the thickness of the wall. The straps-strips technique starts from this consideration to obtain a vertical I-beam through the mechanical coupling between two strengthening techniques. The first technique consists in the use of flat composite materials and in particular of FRP strips. Since friction develops as a reaction to a shear force when a normal force presses the two bodies together, to take advantage of friction, it is necessary to push the FRP strips against the masonry wall. For this purpose, the technique uses the CIM system, a continuous three-dimensional net of stainless steel ribbons. Each ribbon forms a closed loop and compresses the rapid masonry by means of a pre-tension provided by the fastening system. Thus, each closed loop is a strap. Two adjacent straps of the rectangular arrangement provide pairs of equal and opposite components in the plane of the wall. Consequently, the CIM system does not transfer any in-plane force to the nodes, while it compresses the wall along the transverse direction. Therefore, if we place the FRP strips vertically, one in front of the other, on the two opposite faces of a masonry wall, and apply the straps of the CIM system over the FRP strips, the pre-tension of the straps pushes the FRP strips against the masonry wall. The friction developed at the interface provides a mechanical bond that survives the lamination. This means that even after the lamination, the two FRP strips behave like the two flanges of an ideal I-beam, which is a FRP I-beam. Therefore, the strengthening effect under bending loads is the same as that provided by an embedded buttress, with the two great advantages of not having to cut the masonry wall to insert the buttress and not to significantly increase the mass of the building. In the experimental program on the straps-strips technique, the reference specimen for the CIM system is a brick masonry specimen strengthening only by the steel ribbons. Since the pre-tensioning of the straps can damage the bricks at the corners of the loops made by the ribbons, in the CIM system some steel protection elements prevent the concentration of the forces at the points of contact between the straps and the wall. The straps-strips technique replaces these steel elements with 3D printed elements made with PLA, a thermoplastic biodegradable and non-toxic polyester. The 3D technology is less expensive than the traditional hot forming technique in all cases that require the use of elements with very specific geometric characteristics, such as for the protection elements. Even the type of ribbons and the clamping system are not the same as those of the patented CAM system. In fact, the strength of the ribbons was much lower and the ductility much greater, respectively, than the strength and ductility of the straps used with the patented CAM system. The second specimen is the reference specimen for the composite materials, that is a brick masonry specimen, strengthened only by the FRP strips. Lastly, in the third specimen, there are both the steel ribbons and the FRP strips. These are the results of the three-point bending flexural test on the three specimens. The first specimen is separated into two parts with a disconnection under the loading piston that caused the first peak of load, which is also the maximum load of the unreinforced mason wall. Despite the disconnection, the steel ribbons prevented the wall from collapsing, allowing a controlled rotation around the inner hinge up to large openings of the central crack. Actually, due to the high ductility of the ribbons, the specimen did not experience a real collapse, even for large displacements. The maximum load of the second specimen is twice the maximum load of the first specimen. After the peak, the load decreased abruptly due to the delamination of the strips and the wall collapsed. This failure mechanism was very brittle, as it occurs for small displacements without warning. The load deflection diagram of the third specimen has some features in common with the first specimen and some other features in common with the second specimen. In particular, the maximum load is almost equal to the maximum load of the second specimen, but the behavior is as ductile as for the first specimen. In reality, the load deflection diagram of the third specimen is much shorter than the diagram of the first specimen, but the reason is not the collapse of the specimen. Actually, the operator had to interrupt the flexural test well in advance to avoid the damage to the instrumentation, while the specimen could have resisted further displacement increases. The post-delamination behavior of the third specimen shows that the steel straps retain the delaminated strips, which allows the wall to withstand loads higher than the post-peak loads of the first specimen. This happens since the I-beam behavior survives the lamination, although with the reduced stiffness of the transversal link. Since the stiffness of the transversal link depends on the number of straps per loop, increasing the number of straps per loop also increases the load-bearing capacity after the lamination. This suggested increasing the number of straps where the bending moment is greater and performing an additional flexural test. The effect on the load deflection diagram was twofold: a lower load drop after the lamination, with a residual load that is more than twice the residual load of the third specimen, and, as expected, greater post-delamination loads. When the operator stopped the flexural test, the post-delamination load exceeded the delamination load by more than 36%. However, the delamination load increased by only 6%. Since the delamination load depends on the friction activated by the normal forces of the interface, stiffer straps will increase the delamination load. This suggested to replace the steel ribbons with the steel wire ropes. The clamping system of this second combined technique is a turnbuckle, which also allows the pre-tensioning of the steel wire ropes by rotating the metal frame. For the vertical loops close to the middle cross-section, the number of steel wire ropes was increased from 1 to 2. Even in this latter case, the specimen did not undergo an actual collapse, but at this time the delamination load is more than twice that of the second specimen. After delamination, the load deflection curve of specimen W5 falls on the curve of specimen W4, meaning that the two strengthening systems resist the load in the same way after delamination. However, several longitudinal straps suffered fraying and failure, in particular those positioned near the middle cross-section. Each wire failure caused a load drop in a gradual damage mechanism. In fact, when a wire breaks, the other wires support the additional load, avoiding catastrophic failures. However, despite the high ductility of the system, an excessive post-delamination fraying of the steel wire ropes can cause the structural element to collapse. Furthermore, the strap broke the funnel element near the cross-sections of failure, also tearing the break along the wall of the perforated cavity. This made the straps partially ineffective and reduced the load-bearing capacity of the specimen. Therefore, the combined technique has been improved by making two changes. The first change concerns the funnel elements, replaced by toroidal steel rings. The second change concerns the straps, consisting of steel ribbons for the longitudinal loops near the middle cross-section to avoid structural collapse, and an overlying continuous net of steel wire ropes that passes through all the holes. In this last case, the delamination load is lower than that of the specimen with only steel wire ropes because there is only one strap consisting of steel wire rope per loop. In any case, however, the delamination load is almost double that of the specimen strengthened only by FRP strips. Despite a lower delamination load, the load recovered at a given post-delamination deflection value is greater due to the greater stiffness of the steel rings with respect to the 3D printed elements. The fraying of the steel wire ropes begins first, since the number of the steel wire ropes on the middle cross-section is lower. As a result, the load recovery branch is shorter. At the end of the fraying process, all the steel wire ropes broke. However, the specimen still withstands a load of about 6.8 kN, which remains almost constant. This branch corresponds to the action of the steel ribbons that act as life-saving devices, delaying the collapse of the structure. In fact, this load is almost equal to the maximum post-delamination load of the third specimen, which is strengthened only by steel ribbons. The final unloading is a consequence of the slippage that occurred in the shears of the steel ribbons, causing the straps to open. Therefore, the horizontal branch can be lengthened as much as desired simply by using longer ribbons. In conclusion, passing over the FRP strips, the horizontal loops made by the straps establish a stiffness constraint between the FRP strips, similar to that provided by puncture shear connectors. Therefore, the tied FRP strips work as flanges of an ideal I-beam embedded into the wall, giving rise to a strengthening mechanism against out-of-plane loads, and the I-beam behavior survives the lamination, allowing the specimen to withstand loads even when the FRP strips are detached from the masonry wall. Moreover, the strips technique with both steel ribbons and steel wire ropes is the most performing combined technique, which allows us to improve both strength and ductility. In particular, the steel wire ropes significantly increase strength compared to the use of FRP strips only, and in real buildings, this helps protect people from possible impact injuries, while the steel ribbons increase ductility up to the desired displacement value. And lastly, attention must be paid to the resistance of the protective elements to improve the behavior of post-delamination. Thank you for your attention.